The circuit component that we are going to discuss in this and the next few lectures is the OpAmp, which is short for operational amplifier. OpAmps are a fascinating kind of circuit component, and of course it's really not a single circuit component, it's a rather complicated piece of circuitry. In fact, the innards of an OpAmp is so complicated that we are not even going to take a look at that. We will later indicate how an OpAmp works or how you would construct an OpAmp using, say, transistors and other components. But frankly, we will not go into the details of this simply because that would be way too advanced for this particular course. However, as you will soon see in this lecture and the next few lectures, once you take the working of an OpAmp for granted, using the OpAmp in a circuit and designing wonderful circuits, really fascinating circuits using OpAmps, is quite easy. So before we go on to understand what an OpAmp does, let's take a brief recap of what an amplifier is, or in particular what an effective circuit of an amplifier is supposed to be. So this is something we have already discussed before, but let me just remind you that what you see here on the left is a symbol which is often used for an amplifier in a circuit, a triangle with the arrow pointing from the input to the output, and the letter A here just stands for the fact that, or just indicates that this is an amplifier. Now we also talked about the effective circuit of the amplifier, that is what the amplifier looks like from the outside world. So from the source side it looks like an impedance, the so-called input impedance Zi, and from the load side it looks like a voltage source, a controlled voltage source, AVOVI, where O is for open load, in series with an output impedance ZO. And these three quantities essentially are all that you need to understand how an amplifier will behave when you connect a source and a load to it. Let me just remind you once again that these parameters are really effective parameters because they depend not only on the amplifier but also on the external components. For example, Zi depends on whatever load resistance you are connecting, and ZO, for example, will depend on whatever source resistance you have. But in most situations, in fact, as we have already seen in previous videos, such dependence is rather weak, and it's really the amplifier itself which determines, for the most part, what these components are like. And just to remind you that if you were to connect a source Vs in series with a source resistance to an amplifier whose effective circuit we have shown here, and a load resistance across which you are going to take the output, then AVS, which is the ratio between the output voltage VO and the source voltage Vs, turns out to be a multiple of AVO. Okay, let me just write this a bit better. AVO, this parameter here, times two factors which depends on the ratios between the source resistance or the input impedance here and the output impedance and the load resistance. And as we argued, what we want in a good voltage to voltage amplifier, which we are assuming this one is a very large Zi. Why? Because then whatever source resistance you connect, this factor will be almost 1, so the value of the source resistance will have little effect on the final working of the amplifier. Similarly, you would want ZO to be tiny so that even if RL fluctuates, the AVS will not fluctuate, so a small ZO, and you would also want a large AVO. The final one is not so much because you want a large gain, but as you will soon see, if you add negative feedback to a circuit with a large gain, in fact we had already discussed this before, if you add negative feedback to a circuit with large gain, end up with a rather stable gain, which is what you're really aiming at. So these are the three things you want in a good voltage to voltage amplifier. A large Zi, as large as possible. Of course, much larger than the source resistance. That would be great. A very small zero. Again, small means small compared to the load resistance. And a large value of the open loop gain, AVO. Now, an op-amp happens to be as close to an ideal differential amplifier as it gets. So, it's an amplifier, a voltage to voltage amplifier, which has all these desirable properties, as we will soon see. The only new thing here is the word differential. So, we have to understand exactly what differential means in the terminology of an op-amp. Otherwise, an op-amp is just like an amplifier which has as great properties as you would want as listed here. So what does an op-amp really have? First of all, it's a differential amplifier. So instead of having one input, which an ordinary amplifier has, a single input and a single output. By the way, let me just point out that when I say an amplifier has a single input, that doesn't of course mean that you apply a voltage at one point. It always means that you apply the voltage, input voltage, between this point and the ground. Similarly, the output voltage is taken between this point and the ground. The ground is always assumed to be the reference point with respect to which these voltages are measured or applied. So, coming back to the op-amp, an op-amp actually has two inputs. And hence two terminals marked plus and minus. The two input voltages are called V plus and V minus, a single output VO. And as long as the op-amp is working in the linear region, that is, as long as the op-amp is working like an amplifier, the output voltage is proportional not to the input voltage but to the difference between the two input voltages. It's AO, a parameter which depends on the op-amp, which is playing the same role as AVO in the general amplifier case, times V plus minus V minus. And V plus minus V minus is called VD, the difference voltage. So it's a difference voltage VD which is actually amplified by the amplifier. That is why it's called a differential amplifier. And this works as long as the op-amp is in the linear region, that is, as long as it is actually acting like an amplifier. This requires something rather special, making an op-amp work in the linear region, but that's something we will see soon. Now, what does an op-amp have? As I explained, it's an ideal or as close to an ideal amplifier as it gets. An op-amp actually has a very large input impedance, ideally infinity, not infinity really in the real world, but very large. A very tiny zero, again, ideally should be zero, but it's pretty close to zero. And a huge gain AO, ideally infinite, but in a typical op-amp, which you can buy off the market at a reasonable price, the gain is of the order of 20,000 or more. Could be quite a lot more. One bad thing about this gain is that it's rather fickle. Even within op-amps from the same family, the gain actually varies quite a lot. So, if you were to buy, say, an IC741 from the market, which is one of the standard op-amps, general purpose op-amps, this raw gain could fluctuate all the way from, say, 10,000 to 30,000 or more. I really don't know the exact range, but that's, as we will soon see, the exact range or even the exact value of AO turns out to be rather irrelevant. But that's something which we will discuss soon. But these facts that that is a large Zi, a very tiny ZO and a huge gain, coupled with negative feedback, which we had discussed in the last discussion class, this is what gives OpAmp circuits great versatility and precision. And I will try to convince you in this lecture and the next few that because of these properties, it's really a pleasure to design circuits with op-amps. Okay, so now let's consider a very simple circuit. the simplest possible OpAmp circuit, where you just have two inputs, one output of course, but you have actually made life simpler for yourselves by grounding one of the inputs. By the way, the standard convention is, if the inputs are not labeled, then the one on top is always taken to be minus, the inverting input. But just to sort of emphasize that until we get used to the convention, here we are labeling the inputs directly so that you can see that this lower one is a non-inverting input marked plus and the upper one is the inverting input marked minus. Let me stress once again, if an op-amp comes without the inputs marked, then the upper one is the inverting terminal by convention. Well, these are not the only things you connect to the op-amp. After all, an op-amp is an amplifier which amplifies, but it does not create energy of its own. So an op-amp to work must be connected to a power supply. In fact, it should be connected to a typical op-amp. Let's say we are talking about the IC741 here. Other op-amps may have different values for these voltage sources, or may require different values for voltage sources. But the IC741 and many other typical op-amps require a plus minus 12 volt dual supply. What does that mean? It means that this one end has to be held at plus 12 volts with respect to the ground. The other end has to be held at minus 12 volts with respect to the ground. The symmetry with respect to the ground is actually very, very important. It's not enough to have a 24 volt difference between the two ends of the power supply. The power supply really should be plus 12 volts with respect to the ground, another minus 12 volts with respect to the ground. Now, what will this circuit behave like when I change the VI? Now, to understand that, let me just look at the characteristic curve, or in this case, the input versus output graph for an op-amp. The input in an op-amp, remember, is just VD, the differential voltage, V plus minus V minus, and the output, of course, is VO. And as we claimed, VO is A times VD, which is the straight line going through the origin, as long as you are in the linear region. Well, why does the linear region end? The answer is simple. Given the huge gain of the op-amp, even for rather small VDs, what will happen is the op-amp is going to end up predicting, at least this formula for the op-amp, AVD, will end up predicting huge outputs. But the output of an op-amp cannot be arbitrarily big. After all, the output is actually derived from the power supply. So there is an upper limit and a lower limit to how high or how low the op-amp output voltage can go. And this is essentially set by the power supply. It's not exactly equal to the power supply, but it's close. And by convention, we set the upper limit at which the output saturates and does not increase beyond that as plus Vsat, the positive saturation voltage, and the lower limit is called minus Vsat, the negative saturation voltage. Let me warn you about one thing. Although we are calling this plus Vsat and minus Vsat, for a real op-amp, these two values may not be negatives of each other. An ideal op-amp will be perfectly symmetric about the ground, so plus Vsat and minus Vsat will really be negatives of each other. But in real op-amp, these two values may differ in magnitude slightly. But in all cases, these values are sort of limited by the power supply. So what plus minus 12 volt power supply, the plus Vsat and minus Vsat will be close to plus 12 volts and minus 12 volts respectively. Close to, actually slightly smaller in magnitude, typically 11.5 or so volts in magnitude. And let me just emphasize this thing that is written here. The scales on the two axes for VO and VD are actually very different. Remember, the gain of the op-amp, the slope A, is huge. It's around 20,000 or so. So if you were to plot VO and VD on the same scale, this part of the graph, the linear part, would have been nearly vertical. It's actually slightly tilted, but that tilt would be so small that you would not be able to see that if the scales were identical. I've deliberately drawn these things differently. In fact, this side is typically, say, this could be 1 millivolt, let's say, and this would be around 10 volts. So that's a huge scale difference between the two sides, which is just used so that you can see the thing clearly, that there is a slope. However, that should also make this pretty clear that even for a tiny value of Vd, the output is going to saturate either plus Vsat or minus Vsat. So here, let's just say I have Vi of, say, 10 volts. Now, that means V minus, that's Vi, and let's say that's 10 volts. V plus, remember, is actually 0, always, because the positive input or the non-inverting input, which is its formal name, is actually grounded. So what is Vd? Vd is V plus minus V minus, that's minus 10 volts. So you blindly applied the A times Vd formula and taking a gain, let's say, just to be conservative, of 10,000, this would have predicted an output of minus 100,000 volts. That's of course absurd. Because of the power supply limitation, the output will not go beyond minus 12 volts. In fact, it will not even go to minus 12 volts. It will stop somewhere around minus 11.5 or so, because of the drops inside the op-amp. So what will happen if you actually give Vi of 10 volts? That would mean Vd is minus 10 volts, a negative value. In fact, negative value way to that side. But this graph makes it clear what will happen. The output will be minus Vsat. And just for the sake of conversation, just because Vsat sounds not like a very pleasant thing to say over and over again, let's call that minus 12 volts. So when Vi is plus 10 volts, the output is minus 12 volts. What happens when Vi is 9 volts? Again, then Vd, of course, is no longer 10 volts. If Vi is changed to 9 volts, then Vd also changes to minus 9 volts. But again, this does not mean that the output will be minus 90,000 volts. It will be minus 12 volts again, or minus Vsat again. And this continues. Keep on decreasing Vi to 8, 7, 6, 5, 4 volts. You are going to get minus 12 volts as the output. So the output apparently does not change at all. It stays fixed at minus 12 volts. Now what good would such a circuit do? Well, one answer which I often get when I ask this question to students is that this will provide a constant voltage supply, a voltage supply fixed at minus 12 volts. But that actually is quite wrong. As you must realize, the only reason that the output is fixed at minus 12 volts or somewhere close to that is really because the power supply is at minus 12 volts. If this power supply were to fluctuate, so would minus Vsat. So the only reason the output voltage is fixed is because the power supply is fixed. So you already, even without the op-amp, must have had a fixed power supply in order to get this flat output voltage. So getting the flat output voltage, a constant output voltage, is not an utility for this circuit. This circuit will be able to deliver a constant output voltage only if the power supply already provides a fixed output voltage. So if providing a constant output voltage is not the main utility of this circuit, then what is? And the answer is simple. So far we have only been considering positive input voltages. What happens when the input voltage goes negative? Let's say Vi is minus 1 volt. Then what happens is this. Oops. Suppose Vi is minus 1 volt. Then Vd is no longer negative. Vd actually is now plus 1 volt. Of course, a plus 1 volt Vd would have predicted 10,000 volts with a gain of 10,000, with AO of 10,000. But as we have already discussed, you cannot get plus 10,000 volts out of an op-amp. The maximum you can get is plus Vsat, let's say plus 12 volts. So now when the input voltage drops below 0, becomes a negative value, you are going to get plus 10 volts as an output. So to summarize, what will this circuit do? When the input is positive, above 0 volts, it's going to give you minus Vsat, let's say minus 12 volts. And when the input is negative, Vd becomes positive and it's going to give you plus Vsat. Well, there will be a very narrow range of Vi values for which actually this linear formula will hold. But how narrow is this region? Well, saturation will be reached at around 10 volts. And the gain, I have taken it conservatively, is around 10,000. Which means that if Vi exceeds a millivolt, either in the positive or in the negative direction, from 0, Vd will be so big that the output will be driven to saturation. So there's a very, very tiny window over which the output will not saturate, will actually behave like a linear function. That's not something you can actually manage by design. This range is so tiny that if you were to control your voltage from outside, the chances are overwhelmingly high that you are going to get either plus Vsat or minus Vsat as the output. So what this circuit does is something quite non-trivial. It compares the input voltage with 0 volts, the voltage which is being given to the non-inverting end by grounding it, and if the input voltage is more than 0 volts, you get a negative output, minus Vsat. If it's less, you are going to get plus Vsat. So this is why it's called an inverting comparator. And of course, this is comparing with 0 volts only because we have grounded the non-inverting input. If we had actually connected a battery, let's say VR, between the ground and the non-inverting input, let me just stress once again that this is the non-inverting input. By convention, whatever input is down here is non-inverting and this one is inverting. So here the output is going to be plus Vsat if Vi is less than VR, and when Vi goes above VR, Vd becomes negative and the output becomes minus Vsat. So the inverting comparator compares in this case with VR. It compares the input voltage Vi with VR, but when Vi is more than VR, it gives you negative Vsat. That's why this is called an inverting comparator. Just if we were to plot the output voltage versus the input voltage, we will get a graph which looks like this. When Vi is less than VR, you are going to get an output voltage fixed at Vsat. The moment Vi exceeds VR, you are going to get minus Vsat. And this dotted line actually takes the place of what this curve really should be like. This curve has a slope. It's really a continuous curve. It does have a slope, but the slope is so close to being infinitely big. The slope, of course, is the gain of the OpAmp. It's so close to being infinitely big, we cannot really show that on this scale. So this is how an inverting comparator works. Of course, we could have chosen VR to be negative, in which case the transition or the tripping of the OpAmp would have occurred here on the other side of the axis, but it would still have been an inverting comparator because whenever the input voltage exceeds the reference voltage, whatever that is, you are going to get a negative minus Vsat as output. Okay. Well, a comparator does not have to be inverting. It's very easy to figure out how to make a non-inverting comparator. All you have to do is switch the inverting and non-inverting terminal, that is, connect the input to the non-inverting terminal and connect a voltage VR between the ground and the inverting terminal. Notice that here, because we have not stuck to the standard convention that the inverting terminal is always the one on top, we have to explicitly indicate which one the terminals are. The plus on top, minus at the bottom. And what is the output going to be like? The output is going to be plus Vsat if Vi exceeds VR here. So that is the non-inverting part of the name, non-inverting comparator. It compares Vi with Vr, but when Vi is more than Vr, you are going to get plus Vsat. Remember, Vd is actually now Vi minus Vr. So when Vi is more than Vr, Vd is positive, you get plus Vsat. If Vi is less than Vr, Vd is negative, you get minus Vsat. So this is the output versus input graph of the non-inverting comparator. Whenever Vi exceeds Vr, the output jumps to plus Vsat from minus Vsat, which was its value before. Now let us quickly take a look at a slightly more interesting circuit. In fact, the comparator is actually a pretty interesting circuit, but this one, I guarantee you, will be much more interesting than that. Okay, I have not actually drawn the output versus input graph for this circuit called the Schmitt Trigger completely right now, but let us just try to understand what it will do. Here, notice that what we have done is we have actually connected the output back to the positive input. Once again, this is the positive input and this is the negative input. The output has been connected back to the positive input via a potential divider arrangement between the resistances R1 and R2. The input, as in the inverting comparator, is connected to the inverting input. Now, let us just try to understand how this circuit is going to work. Let's say I have given a large negative input to Vi. Let's say Vi is minus 10 volts. Whatever VO is, a fraction of that VO will be fed back to the positive input, and Vi is definitely going to be less than that. So what that means is now output is going to be plus Vsat. And this will continue. Of course, if the output is plus Vsat, what is the voltage here? The voltage V plus is going to be Vsat, the voltage here, plus Vsat, into R2 divided by R1 plus R2. Simply, the output potential, VO, in this case plus Vsat, is divided by this series potential division circuit. Well, why is this a series circuit? After all, isn't there another branch here to the OpAmp? The answer is, well, the OpAmp has a huge input impedance, so it draws very little current. So for all practical purposes, and we are talking about practical purposes here, what we are going to do is we are going to treat this current as inexistent. What that means is whatever current flows through R1 is the same as the current which flows through R2, and that is exactly what you need to have a series circuit. So V plus is at this value, and which we call VUTP. UTP stands for upper trip point. There is a voltage at which the output trips. This is the value of the input voltage at which the output trips from plus Vsat to minus Vsat. Why is this called the upper trip point, and how is this different from a comparator? That will be clear very soon. So just to repeat, you start with a large negative value. The output voltage will be plus Vsat. V plus will be sitting here at what is called the upper trip point. And as long as Vi is less than that value, so if you keep on increasing Vi, as long as Vi stays less than VUTP, the output is going to be plus Vsat, and the moment Vi exceeds VUTP, the output trips to minus Vsat. So far, this is exactly what was happening with the comparator. But now, let's think of what will happen if we start decreasing the input voltage. So we are going back. The input voltage is decreasing. But now notice what happens to the V plus. V plus now is no longer VUTP. the output voltage is no longer plus Vsat, it's minus Vsat. So V plus is now minus R2 Vsat by R1 plus R2. What that means is this is no longer VUTP, a different voltage, a negative voltage actually, and that's called VLTP. That's the lower trip point. So what you have is that the as you keep on decreasing the input well beyond VUTP, the output stays minus Vsat because the circuit is now comparing Vi not with VUTP but with a different voltage, VLTP, which is the voltage at the plus end now. What will happen once you reach VLTP is that the voltage is going to trip to a positive value, to plus Vsat. And then the voltage is going to continue like this. But notice that in between VLTP and VUTP, if you have a voltage value of input voltage between these two ends, then something rather strange happens. If Vi is less than VLTP on this side, the output is definitely plus Vsat. If Vi is more than VUTP, the output is definitely minus Vsat. But if Vi is somewhere in this range, somewhere between the two trip voltages, then what happens is that the output will depend on history. Will the output be plus Vsat or minus Vsat? That depends not only on the current value of the input voltage, but on how the input voltage changed while it got here. Was it coming from a large negative value, in which case the output will be plus Vsat, or was it coming from a large positive value, in which case the output will be minus Vsat? So what you see here is an example of a phenomenon which is very familiar in physics. It's called hysteresis. You have seen this in magnetism, but what hysteresis really means is history dependence. The output depends not only on the current value of the input, but its history. It depends on how the input acquired its present value. So the Schmitt trigger is a very, very interesting circuit because its output depends on the history of the input and not just on the current value of the input. So you don't really have an input-output graph here. You can only draw graphs for functions where a given value of Vi will only produce a fixed value of Vo. Here, what you see is Vo can take different values for the same value of Vi. This hysteresis behavior makes the Schmitt trigger a very, very interesting circuit to work with. Okay, so the Schmitt trigger demonstrates hysteresis. That is an interesting thing in its own right, and comparing it with the other physical systems which show hysteresis may very well give us some insight. But are there any practical applications of this circuit? It turns out that there are plenty. Let me just give you a couple of them. One of the applications of the Schmitt trigger is essentially to produce an improved comparator. Let me try to explain what I mean. A comparator, of course, as we have seen, compares an input voltage with reference voltage, and whenever the input voltage crosses that reference voltage, the output switches sign. So you could actually say connect a LED, light emitting diode, in series with a resistance across the output, and the diode will glow only when the input is below the reference voltage, indicating some kind of trouble with your circuit, or indicating that you need to take some corrective action, and will not glow when the input voltage is above the reference voltage. Or you could do it the other way around as well. In fact, you could even use two diodes connected back to back, two light emitting diodes with different colors, and the color of the diode which glows will indicate what kind of voltage you have. Are you below the reference or are you above the reference? The trouble with that kind of comparator circuit is that it's very prone to noise. Sometimes the input voltage might fluctuate just because of some random noise. Maybe somebody threw a switch, and because of the switch, coming in, there would be transients in the circuit that would make the input voltage go up and down a bit by a small amount. But notice that for the comparator, the switching will happen whenever the voltage crosses the reference voltage by as small as a millivolt, or in fact actually even smaller. The millivolt that we found out earlier was assuming that the gain of the op-amp was, the raw gain that is, was of the order of 10,000, which actually is an underestimate for most op-amps. So the moment you cross the reference voltage by a tiny amount, the output is going to switch, and this might very well happen because of noise. Let's say we have a circuit where we know that the noise is of the order of tens of millivolts. And if you are close to the reference voltage, then there's every chance that the noise, which goes up and down randomly, would cause the output to switch randomly, and that would be a very bad thing. On the other hand, if you use a Schmitt trigger, where the center of this hysteresis loop is at V reference, and the width is controlled carefully so that any noise will be within the hysteresis loop, just think about it. Then the output will switch only if you cross the threshold and go beyond the threshold and cross over to the other side. That is, you have quite a lot of buffer within which the output will not switch despite your crossing the reference voltage. By the way, this particular Schmitt trigger that I have drawn, this circuit, it's obvious that it will be centered. The hysteresis loop for this will be centered at 0, because the two trip points, the upper trip point and the lower trip point, are equally spaced on the two sides, assuming of course that the saturation voltages are identical on both sides, or negatives of each other, to be precise. How would you produce a hysteresis loop which is biased somewhere else, where the center is shifted and it's not at 0? And the answer is simple. All you do is, in addition to this R1 and R2 combination, you put a battery here. That is, you put an extra voltage, and it will take very simple circuit analysis to figure out that then the upper trip point and the lower trip point will not be at these values, but they will be shifted. And that's all you really need to shift the hysteresis loop to one side. Of course, you could put a battery biasing this end to be positive or this end to be negative. That would help you to shift the hysteresis loop either to the right or to the left. So that is one application, protecting your comparator circuit from random noises so that your circuit actually responds only when the output exceeds the reference value by quite some amount, and then stays there once it has exceeded, even if random noise drives you below the reference voltage. Only when your random noise drives it substantially below, or rather, only when an actual signal drives it substantially below, because the width of the loop has been chosen by you, so that random noise should not be able to drive you from one side of the loop to the other side. Only when the signal is large enough do you get a tripping, that do you get the output voltage to change sign. So that is one application that you could use the Schmitt trigger for. Another rather interesting application is one in which the Schmitt trigger is part of the circuit. Let me just show you what the circuit is. The circuit is the one on the left here. This is really the Schmitt trigger, at least this part. If you leave out the R and the C here, the rest is just the Schmitt trigger circuit that we have been seeing so far. Instead of the input voltage here, what we have done is we have taken the output, passed it to an RC combination, and connected the capacitor voltage to the negative input. So this is the Schmitt trigger with the input provided by an RC network. Now let us try to analyze what this circuit will do if you were to switch it on, assuming, let's say, the capacitor is uncharged at the beginning. So you just throw the switch, the power supply comes on, and what will happen to this circuit? I'm going to sketch this out here, and for the sake of, well, to make it easy for ourselves, I've already drawn in some nice voltages. The plus Vsat and minus Vsat are the voltages which the output is going to swing between, and these two voltages that you see drawn here are simply the upper trip point and the lower trip point. for this particular circuit. Now, let us see what will happen to the capacitor voltage when you switch on the circuit. And let's draw this in purple. So, the capacitor is uncharged to begin with, and when you switch on the circuit, let's just say, for the sake of definiteness, that the output goes to plus Vsat. Remember, the two voltages at the two ends, there is no guarantee that it's going to be equal to begin with. There will be some voltage at one terminal which will be more than the other. So Vd will be either positive or negative. So depending on the random connections, the output will be either plus Vsat to begin with or minus Vsat to begin with. For the sake of definiteness, let's just say it's plus Vsat to begin with. Then, the capacitor will be in a situation like this. It's uncharged, is connected via resistance to a voltage V0. And although there is another branch here, remember that the op-amp has huge input impedance, so it does not draw any current. So this RC is really a series RC circuit, something we have studied a long time ago in our course. So what does the capacitor do? It starts charging up. So it charges up according to the standard RC series circuit charging rule. Of course, it's charging as if it's tending towards plus Vsat, because that's where it wants to go, but it doesn't go all that way. Why? Because once the capacitor charges up and the voltage of the capacitor, which remember is V minus, the input to the Schmitt trigger, once it crosses the UTP, the upper trip point, the output suddenly switches to minus 12 volts or minus Vsat. Okay. So what happens now? The capacitor, which is at the upper trip point voltage, is now connected to a negative voltage on this side. So it starts discharging towards minus Vsat. So it will actually try going this way. Of course, this is an exponential curve. You have to assume that what you're seeing on the screen is an exponential decay curve and not the crude thing that I have drawn. But once it reaches the lower trip point and tries to cross beyond that, of course it will not cross beyond that, because once the input voltage reaches the lower trip point, the output switches back to plus Vsat, and now it's going to charge up again until it reaches the upper trip point. So the first half of the cycle is really atypical. In all other cycles, what will happen is the capacitor will charge up to the upper trip point, output voltage will switch to minus Vsat, and the capacitor will try to discharge towards minus Vsat, so it will get an exponential decay curve which would have actually saturated at minus Vsat. It doesn't go that far, because the moment the voltage reaches the lower trip point, the output switches back to plus Vsat. The capacitor starts charging up again exponentially, again going all the way towards plus Vsat as saturation, but can't go that far before it reaches there. The upper trip point is reached and the voltage has to switch back again. So what will the output voltage behave like? Well, let's plot that. The output voltage, by assumption, was let's try a dashed line style. Was plus Vsat here. But then, the moment the capacitor voltage reaches upper trip point, it switches to minus Vsat and stays at minus Vsat until, not all the way up here, sorry. It will stay there until it reaches this. So this is this voltage. Then it switches back to plus Vsat. Then it actually stays at plus Vsat until the capacitor charges up again to the UTP. And, well, if you pardon my rather bad drawing skills, if I really had the curve drawn properly, this would have been more curved like this, and this would have hit the curve here. Maybe, let me just give it another try to draw this better. Let's go back to the purple style with dotted lines. I'm not, oh, sorry, now I have a worse thing. Let's try this. Okay, of course this is not much better as far as the freehand curve goes, but you get the idea. This is what is going to happen. And of course the curve really tries to continue beyond that, but doesn't get a chance to. Then it comes back again. But what is really going to happen is, if you ignore the first half cycle, after that is going to be completely periodic. And you should easily be able to recognize that the time it takes for the capacitor to discharge from the from the voltage at UTP to the voltage at LTP going towards minus Vsat is the same as the time it takes for it to charge from VLTP to VUTP going towards plus Vsat. So these two cycles are actually equal in length, in time of course, and then this keeps on repeating forever. So what you get is a nice square wave output which switches between plus Vsat and minus Vsat. In fact, if you take the capacitor voltage, output voltage, you also get a periodic waveform which is slightly curved, but that gives a pretty good approximation, which is decent enough for many applications, to a sawtooth wave, that is something which goes zigzag. So this circuit actually gives you an oscillator which produces a square wave, and as well as a triangular wave generator. Not really a sawtooth. A sawtooth is one in which the rise is sharp and the fall, rise is maybe slow and the fall is sharp. Here the rise and fall are equal in length. So this is a triangular waveform generator. So as you can see, we have made an oscillator with just an op-amp and a few circuit components. A very, very cheap oscillator which is actually quite a good and stable one. You can use it for many practical purposes. Okay, what will the time period of the oscillator be like? Well, I will allow you to calculate it for yourself. Just as a standard RC circuit charging and discharging calculation. But let me point out one thing. This oscillator will always produce a symmetric square wave. Okay, what will the time period depend upon? The time period, of course, will depend on how long it takes the capacitor to charge up from LTP to UTP or down from UTP to LTP. And that, of course, is connected. The time it takes will be connected to this. It will be connected to RC simply because that's what controls how fast the capacitor charges. There's a time constant for the capacitor. In addition, it will also depend on the R2 by R1 ratio. Why? Because the upper trip point and the lower trip point voltages, the voltages this capacitor charges or discharges to, is actually controlled by R2 by R1 ratio. So if you change the R2 by R1 ratio, the capacitor gets to charge more or less, and that will of course control the time it takes. But one important thing, this circuit will have the output at plus Vsat for as long as it is at minus Vsat. Once again, ignoring the first half cycle, that, as I said, is atypical. Every subsequent cycle will be equally divided between plus Vsat and minus Vsat. What if you wanted an asymmetric cycle? Somewhere maybe it was plus Vsat for more time, minus Vsat for less time. For that, what you will have to do is somehow cook up a way that the capacitor charges up more rapidly, say, than discharges, or the other way around. Let this be a puzzle for you. Try to figure out how to achieve that using circuit components that you have already learned about. Okay, so far we have seen several applications of the op-amp in circuits, and there will be many more in the lectures to come. But you must have noticed one thing about all these circuits that we have seen so far. In all these circuits, the output was not really proportional to the input. The output swung from plus Vsat to minus Vsat in all of these cases. More importantly, a very small change in the input could produce a big change in the output. Or of course, the last circuit that we saw was not even an input-output scenario. it had no input, it produces a square wave output on its own. But if you leave that one aside, all the other circuits we have seen so far does have an input and an output, but the input-output relationship is not a smooth one, not a linear one. So these are examples of what are called non-linear circuits. So the op-amp in these cases is not really working as an amplifier. An amplifier is a circuit in which the output is proportional to the input. And you can easily see why it is not. The op-amp is in fact a great amplifier, as we have said at the very beginning. Why? Because it has a huge input impedance, it has a very low output impedance, and to top it all, it has a huge gain. Funnily enough, this huge gain which the op-amp has prevents it from behaving like an amplifier in all these circuits that we have seen so far. The gain is so big that even for a very small input voltage, the output just swings and goes to either plus Vsat or minus Vsat. So rather ironically, it is the huge gain of the op-amp, which we touted as a great thing for it to be an amplifier, is exactly what is preventing it from behaving like a decent amplifier. The nonlinear circuits are very important, and we will see several more nonlinear circuits involving op-amps in the lectures and assignments to come. But none of these are actually amplifiers. None of these are circuits in which the output bears a linear relationship to the input. And that is, of course, quite troublesome. Don't we have linear circuits using op-amps? Actually, we do. In fact, most of the circuits that we are going to discuss are going to be linear circuits. But you have to realize that in order that the op-amp behaves linearly, the relationship that we have talked about, that is VO is A0 VD, where VD is V plus minus V minus. This should work. This works only when the op-amp is in the linear region. And the trouble is, op-amp will be in this linear region only as long as VO has a magnitude which is less than Vsat. Once again, I am assuming that plus Vsat and minus Vsat are really equal in magnitude, although, as I have explained before, there may be small differences. But just for the sake of simplicity, we are assuming that plus Vsat and minus Vsat are really negatives of each other, as the notation suggests. So mod VO less than Vsat. And what does that imply? That implies VD must be very tiny in size. Why? Because VD, after all, in the linear region has to be VO by A0, and A0 is huge, and VO in the linear region cannot go beyond plus minus Vsat. In fact, VO cannot go beyond plus minus Vsat even when you are outside the linear region. But in the linear region only, this relationship between VO and VD works. So, if you want to keep the op-amp in its linear region, that means you want to make it work like an amplifier, you have to ensure that VD is tiny, somewhere less than a millivolt, or actually even less, depending on how good your op-amp is or how big the op-amp gain is. Now, if you were to apply two different voltages at the two inputs of an op-amp and hope and pray that they came so close to each other that VD was tiny enough for the op-amp to work in the linear region, then almost certainly it's not going to work. It's going to be very unlikely that two voltages which you independently put at the two inputs will come so close to each other that the op-amp will be in the linear region. So in order to make the op-amp work like an amplifier, that is, work linearly, you will have to actually do something to ensure that VD is very tiny. And that something is something we have already met in a discussion class, that is negative feedback. That is what we are going to discuss next. Bye till then.